Neuroeducación de la Universidad Libre de Bolzano, en Italia. Su actividad investigadora principal se centra en el campo de la planificación visoespacial, las funciones ejecutivas, la memoria prospectiva y la memoria de trabajo, así como su relación con la educación y las nuevas tecnologías, como la realidad virtual y el pensamiento computacional. Sus intereses científicos incluyen el estudio de los factores humanos, las habilidades para la vida y el bienestar. Demis, whenever you can share your screen, and this is your audience.
Okay, great. So, first of all, thank you for this invitation. This is very exciting for me to talk to foreign audience. And given that the topic of let's say, that was assigned to me was to talk about the connection between neuroscience and education, I thought that it was very, very broad. Therefore, I decided to turn down to one example, to one application of how neurosciences could be reliable and could be good in order to develop knowledge and could be used in school as well. Therefore, this title may be kind of, let's say, foreview about what I'm going to say, talking about little blocks for great achievements, breakthroughs, based obviously on a neuroscience approach. Well, let's talk about one of the toughest fields, toughest subjects that we all have experienced in our scholastic career, mathematics. So let's start evaluating whether for us and for all the people that are around us, mathematics was difficult or not. Then we are going to evaluate some aspects related to cognition that could be useful to go on evaluating the proposal of mine, but not only of mine, but also the group that I'm working with about, say, a game. Then we're going to end up with conclusions, and I hope to leave a lot of time for discussion. That, in my opinion, is one of the most relevant part of a discussion, of a conference like this. Obviously, if you like to, you can open your mic and make questions during the presentation. And there would be other opportunities for me also to ask you to open a mic, for example, by asking you whether you feel that mathematics is difficult or not. And then tell me why. So please open your microphone.
Well, in my opinion, hello.
Hello.
I think that mathematics is very beautiful. I keen on mathematics, and I think that it's not difficult because it's a question of understand the procedures of the numbers. It's not like history that you have to study and making hours studying. It's a question of understand the techniques,
Concepts and procedures.
Yeah.
May I ask you whether understanding mathematics is difficult or not?
Probably it could be difficult for students because mathematics is an abstract concept. So probably depending on the level of the students, I think that it could be quite difficult. But I think that the key is regarding to the techniques that teachers use to explain these concepts.
So maybe not because mathematics is difficult on its own, or the cognitive process is needed in order to learn and use mathematics, but maybe a lot of difficulties may descend from what teachers have done in order to let us approach mathematics. That's your point, isn't it?
Yeah, that's it. Yeah.
Okay. Are there other comments, other points? También en español.
podéis hablar en español porque Demis os va a entender perfectamente en español. Para mí, las matemáticas...
No lo creo, pero...
Perfectamente. Pero si no, traducimos. Yo sí creo que las matemáticas son difíciles, creo que son muy complejas, os enseñan de una forma muy compleja en un muy mal momento evolutivo. Yo he entendido más matemáticas cuando he dejado de estudiarlas.
Yeah, that may happen not only to you, but also to many people that then discovered how mathematics can be beautiful and can be useful also because of a job, because they found a position or they need to work on a field in which mathematics is necessary. Therefore, you cannot avoid mathematics. And then sometimes you find that mathematics is not that abstract, not that theoretical as you were thinking so far. According to different papers, if you can go on, well, there are three main reasons that people describe as being their answer to whether mathematics is difficult and why. So, because maybe it's too theoretical and it includes too many abstract things that are not connected with reality. Therefore, you cannot find a real application of this knowledge. Then another source of problems may come from the many rules that you need to learn. That maybe there are abstract rules, but also concrete rules, so algorithms, but you need to be precise. You need to be very, very tight to the program. And therefore, you cannot allow errors to happen. And therefore, mathematics you feel mathematics to be kind constraining. Therefore, you cannot escape from mathematics. If you are just making a little error, you're out of the correct track. Therefore, you feel anxiety. You feel that is field, and therefore happens what Seligman said, that you cannot act anymore because of that fear. Another source of problems may come from those that have not developed memory enough. And it happens that maybe teachers are talking about something that for them is maybe easy to remember, a list of 5 elements. However, what is the memory span of children? On average, it is 5, but it happens that average may include outlier, so people or children with a memory span of 8, 9 items, but also children that have a memory including 4 or 3 items. Maybe they are not, let's say, not impaired. It's not a problem. It's maybe a phase, a moment in the evolution. So you are going to recover that that gap soon. But at the moment, you feel yourself being not able to do as the other people are doing. And the teacher is quite surprised to see that you cannot remember these 4 things. Well, you have not studied enough. You did not pay too much effort or enough effort in order to do that. It's not because of a problem of memory or a memory that is not developed enough. And for example, talking about perspective memory, the one that is mainly used to remember to do homeworks, well, it may happen that given that it is tightly connected with the development of the frontal lobes, it completes its development only at the age of 11, 12, 14 years. And it happens obviously that it starts its development even at the age of 1, 2 years old, but you cannot really manage it as an adult may do. Therefore, you need memory in order to remember rules, and to recognize what theories may be applied in that situation. Therefore, for many of us, mathematics has resulted to be difficult and a source of anxiety. However, given that we are talking about conceptual knowledge, that's not difficult for us. It's not that difficult. It depends on also the colleague of us before I said on how this is motivated. Just one step back. He was saying that mathematics is not as history, while you have to just simply study all the facts. While I think that you may be surprised to realize that also history needs a lot of understanding, because you need to create connections, you need to provide explanations. Therefore, you need to use a lot of understanding about the facts that you are studying. Otherwise, it's a simple list. I'm currently working with a PhD student in history, and we were discussing upon this topic as well. Therefore, I'm sorry, but we need to restore some aspects about mathematics and history as well. Then, we need not only to know concepts, but also procedures. We need to know why this procedure instead of the other one. But we need to know also what is this procedure made of? How are the several steps in this procedure connected with each other? And obviously, how can I remember them in the correct order? That's about it has to do with memory and planning as well. And on a certain moment, we need also to retrieve something from the memory, from the long-term memory, in order not to spend always a lot of time in solving always the same problems with the same, with the same data. Because if you can exploit something, something that was already solved, it is easier and it is faster. Therefore, memory, long-term memory in this case, is a strong vehicle for being effective in mathematics. Not only mathematics, but in general, all subjects. However, because of these reasons, we may say that mathematics could be difficult. The point of mine, however, is to disrupt this connection. Not only because mathematics, you may like mathematics, but it's because mathematics intrinsically may have some points that are against this, this prejudice against mathematics. So let's talk about the first one. Is mathematics too abstract for us? Well, let's consider this formula. You know what this formula is about? Open your microphone. What do you think that this formula describes?
I think that this is an equation, and this is an equation of a line in a graph.
Definitely, you're right. Here it is. It describes, and thank you for your answer, because it is maybe in a high level, level highest respected to the primary school, but I think that the relationship with mathematics cannot be separated into different chunks depending on age. I will come back to this point also later on. But indeed, it's a law that starts that describes the relationship between the x-axis and the y-axis, in which some measures can be taken about, in this case, 2 points. So if you obtain just the evaluation in x and y for 2 points, you can create a segment, a line connecting the 2 points, but you can also describe a relationship. A relationship, in this case, between X and Y. Therefore, you go on creating a line. You go on creating a line that in this case is describing not only what happens between the 2 points, but also outside of the 2 points. So it's something that by using a theory between or a calculation between the two variables X and Y, it creates a way to evaluate something also beyond the data that we have. And talking about relationships, well, let's consider something that is not on mathematics. Let's consider something that is on the correct way to consider a relationship if you're talking with a person. So let's talk about, let me check the pen here, and the color maybe a bit darker. So let's consider relationship between one person and another person. Maybe, for example, between a woman and a man. Let's consider activities. So when I do not like, what can I say, meat, and also the man does not like meat, we put a point here. When I like, say, go shopping, and the man does not like go shopping, it goes here. When I like something that maybe it's in, yeah, I do not like that much, but I do not dislike, and the man as well, the point is here. Then if we both like going out for dinner, well, it is here. That maybe there could be also other activities that may describe the situation. So on a certain point, we can go on drawing a line that may summarize what is happening between me and that person. However, that is feasible, possible, just as mathematics said, because that is an estimation, and you have a certain error that is connected because there are some points that do not fall directly on the line. Therefore, it may happen that relationships, let me check whether I can delete everything. Eraser. Here it is. It may happen that if the relationship between one person and the other person may include something that they both dislike, something that they both like, but then a lot of things that in which the two persons are not going the same direction, it may happen that the cloud of points is quite random. Therefore, mathematics tells you that you cannot create one single line. So you cannot really describe what is happening. Could be the line this way, that, this one, or maybe a kind of a wave. So whatever line may describe let's say, a chaos like this one. Therefore, mathematics can allow you to predict also what may happen, what you may see, but also starting from some data that you are going to collect. It's very important to know how to draw relationships in mathematical form, because if there's a possibility to do that, you are far more skillful than other people in order to predict what is going to happen afterwards. And that is definitely not an abstract aspect. It's a very concrete aspect, because those that are more able to predict what's going to happen are those that are paid better. And that's something that other people may recognize. Okay, then let's go on to the second aspect, procedures. About mathematics, you find here a problem that is generally found in later age years of the primary school. So to know how fractions are on the line. So for example, here you can simply define the line by including the numbers between 0 and 10 and by putting a comma in front of them. So 1, 0.1, 0,2, 0,3, and so on. Therefore, you can create easily a line with a child that is quite straightforward. The main problem is whether you have to include fractions that are not based on 10. For example, 1/4. Is 1/4 more or less than 1/5? Well, that is a very tough task. Generally, you know that 4 is a lower number with respect to 5. However, whenever it is down in the fractions, the opposite is the correct answer. Therefore, you need to know how to manage this, let's say, this problem, and therefore it's quite difficult to understand fractions, given that maybe many of them do not have the underlying number that is so nice as 10. The problem in this case is very tough. Or could you find examples in real life in which this is not definitely a problem? It has to do with money as well. Oh, let's consider cents for the euros. So you may find that there could be 1 cent, 2 cents, 5 cents, 10 cents, 20 cents. Okay, let's ask children to evaluate how many coins are needed in order to create one of these objects. So 1/5 of €1. Which coin would you pick? 1/5 of €1. So maybe it means that I have to divide the euro into, I have to obtain 5 coins in order to obtain an euro. And here it is. It's quite straightforward. Okay, let's talk about 1/4. Oh, do you have here a coin? Well, not, but you have 4 of these in order to create €1. Oh, it's very difficult because I cannot see here any coin. What would you need in order to create this coin? Oh, well, a coin of this kind and another one of this kind. Okay, then. So now compare. Which worth more, 1/4 or 1/5? Straightforward. Why? Because it includes a process described in the 70s by Watson and Legrenzi, talking about reasonment. That they were creating a kind of strange task using letters that were open or closed with a mark or not. But they were evaluating a strange process in humans that when they have to do tasks based on logical decisions, if the material is abstract, they fail. If the material is concrete, they succeed. Oh, so mathematics, if the procedure is described in a theoretical way, it does not work. Oh, do we need experiments to know that if a procedure is theoretical, that is difficult? A procedure needs to be used. So you need to be concrete in describing procedures. You cannot make examples that are more complex than a theory itself. Yeah, let's go on to the third one about memory. Facts in our memory, one of the most known is the table or the Pythagorean table. Here you can find an example. Well, it is not straight, it's tilted. There's a reason afterward. But do you know how to compute 6 by 7? What's the result? 6 multiplied 7 times. Yeah, I think that you don't need to review what's the result on the Pythagorean table to know that the result is 42. Do we need to explore the table, or did you just get the result from your memory? 6 by 7, 42. There are some other facts that are more that are easier and other that are more difficult. A study of Campbell in 1993 has divided all the cells of the Pythagorean table into easy calculation and difficult calculation. One, say the most difficult one is 7 by 8. A lot of errors goes around there. But the problem is that we use our memory, but that is the goal of learning. Because at the end of learning, we obtain a well-made fact in our memory, that is this table. We don't need to go on revising line and columns, but we directly point to the crossing cell in order to collect the result. And that is what we do. But that is happening in the end and after many years that you have used this method, because the Pythagorean table is still a procedure that becomes a fact because of the learning that we are doing on this. What happens before learning? There's no facts. And therefore, you need to create it. You need to create a frame and create the content. So, in order to have a fact in the end, well, it's not a fact in the beginning. You need to create it. You need to work. You need to learn. And generally, you start by creating a frame which includes a certain number of columns and the same number of rows. And you put numbers in that, numbers that you already experienced. So the number between 1 and 10 are known on the two lines. So for example, here and here. However, maybe you can make a calculation by heart on this square because it's quite easy. It's maybe not that easy, but quite easy as well. Also, these two squares that are symmetrical. The toughest part of the table is this one, in which also a lot of cells are in the study by Campbell in the difficult side of the table. However, let me check whether there could be other aspects of the table that were not explored so far. So think about the table here that is tilted to some extent. Try exploring relationships on the diagonal. What's on the diagonal? Open your microphone. Try describing, try answering step by step the question of mine, evaluating whether that in the end could be another way to explore the table. What's in the diagonal?
En la diagonal habrá resultados fáciles y resultados difíciles.
¿Por qué?
Porque abarca los cuadrantes fáciles y los cuadrantes difíciles.
Ajá.
Si exploramos la tabla en diagonal.
And 6 multiplied by 6, what does it mean? 8 multiplied by 8, what is it?
Exacto, sí, sí. La línea diagonal.
Sí.
El número por sí mismo. El
Por sí
cuadrado.
mismo. El cuadrado. Here they are. So on the diagonal, you can see all the squares, the results of the multiplication of the number for itself. So they are squares. So they describe always squares. The other numbers describe always rectangles. But there's also another property of the table. Look, this number and this one number is the same, obviously, because it is on the line, on the first column and first row. So it needs to be the same, but what's in the middle need always to be higher. But take a look of this 2 and 2, 3, 4, 3, 4, 6, 6, 4, 5, 8, 9, 8, 5. It increases step by step, but always keeping them on this diagonal, the highest number in the middle, and then it is symmetrical. It's something that we do not, we already know that is symmetrical, but it is symmetrical in the differences also on this side. So for example, 2 by 2, 2 and 2 are the same. 90 and 90 are the same. Talk about 3, 4, and 3. The difference is between 3 and 4 is 1. So this is 1 unit lower than 4 and 1 unit higher than 3. Also here, 80, 81, 80. 4, 6, 6, 4. It is 2, the same, minus 2. 70, 72, 72, 70. Oh my God. There's another property of the table that I didn't know. I discovered while I was making the presentation. Yes, and how that could be useful, because it is another way to create the table and to put elements inside. It is based on the exploration of the table. But what does it mean that you are exploring the table? That you are managing the table? That you are manipulating the table? That you are making things? And what do you do with things? Generally, they are objects. And facts are still objects, mental objects. But the way that you are interacting with objects, with your hands, by doing something, is the way that you do things with your mental objects. Therefore, the more you manipulate your objects, the more you learn how to use them. And here is just an example that you can find on the internet, but you can find a book full of these kind of examples on how these are problems in the real life that can be solved by using the Pythagorean table. Let's talk about the chocolate that I really like so much. If we have 4 children, how many squares do you think that every child is going to receive? 4. Oh, 1, 2, 3, 4. So 1 line, obviously. So how many? Well, you now count how many squares, how many bytes are here on 1 line, and then that's it. The problem is when there's a number that is not in this table. What do you do if there are 5 people? You turn back to the calculation, but you already knew that, because if there's a possibility to use the table, is whether evaluating whether some calculation is in the table, so it is quite easy to use that method, or is not in the table and you need to use another method to calculate that. And therefore, the use of facts in our memory can be first evaluating whether I can use facts or not, and then when it is possible, then I can explore it. Then numerical cognition is something that can be relevant to know, because the facts in memory are included in this verbal code, while calculation in, let's say, precise calculation are included in, while you have to use the verbal code, the visual code, and procedures to the Arabic numbers. While if you have to make estimations, you use this method, the method based on this part of the brain as well. Another aspect that could be relevant is the numerical sense described by Brian Butterworth. And one example made with fishes, in which if there's a fish in a bowl like this, and there are a certain number of fishes in this part, and another number of fishes in this part, the fish is intimately likely to go to the most to the biggest group, because it increases the possibility to survive. Therefore, fishes were studied, and they shown to have an intrinsic ability to count and to distinguish numbers. So mathematics is not something that is just a cultural fact. There are some aspects of numerical cognition that we have pre-installed, and therefore we need to find a way to develop them in a way that could be consistent, congruent with the brain that we have and the way that generally is developed. Therefore, that is another fact that may be useful for my speech later on. Cognition about the movement. It's mainly the topic of the World Conference here, but I would like to focus and spend not too much time, but to focus on two aspects. Try looking to the representation on the motoric cortex about the most relevant part of our body, face and the hand. So, if you have to interact with the environment, what is considered to be by our brain the most important part of our body? The face, but also the hands. And if you can see here also the representation of the embodied cognition, well, you cannot see really many things about the person. You can see a head with the brain, obviously, and the hand, and what is written here, body. So you interact with the world according to the representation of the embodied cognition by using the brain, so the eyes, the mouth, the part of the face, the head that you turn, the ear, but also the hand. So maybe the hand is something that is particularly relevant for understanding the world, maybe numbers as well. Then motivation is always said to be really relevant. According to maybe not that recent, but maybe a theory that was not included in many in many textbooks about the most relevant theories of motivation. But I found that this theory is particularly straightforward, including 6 basic motivations that cooperate or interact with each other, developed through our, let's say, through our history, not something that we are now discovering day by day with the learning. And I would like to put the attention onto 3 of them. That's cooperation, particularly relevant when you would like to make people interact with each other. But people interact with each other also in competition. It's always been seen as something to be avoided, competition, because it is not fostering learning. Because you make people or children to compete with each other. Yeah, but that's the wrong way in which competition could be used. Because competition is the thing or the motivation that can bring you to success. So, for example, if you create a competition between me and the task, it's still a competition, but it's still in favor of learning. And then the one in which learning is included as part of is the exploration. And generally, when people is curious, when people would like to know more about something, when the people play, they are using the exploration system. But generally, according to the previous series about Bowlby and colleagues, exploration starts only when the attachment system is satisfied. Therefore, if you're not hungry, if you have slept enough, then you can be happy to play with. To play with. Let's play with. Here is a picture of a game that I've discovered due to a colleague of mine, and that is quite resembling a game that I found very, very interesting when I was at the kindergarten, that I cannot find in any other place. I don't know whether it is sold anymore or not, but I found this being a good supply. It is made of cubes that you can bind in all the different directions. But let me stop the presentation and let me show directly what I have here in my room. So here is say a box in which there are some of them, and let me show something directly, because maybe it would be good to evaluate what is this about. So here you have cubes. Let's take one that has a different color, that could have some pins and some holes. Therefore, you can bind them just once to another one, but you can create chains like this in order to create structures, three-dimensional structures, for example, that you cannot do with the normal Lego objects. There are some examples that I can show you of what can be done, because there are also other aspects, other objects, for example, gears. And therefore, maybe you can create not only for mathematics, but also for movement. But about mathematics, let me describe something that you can do at school. For example, let's take I'm sorry. Okay, here we are. So here you have an example of a kind of very easy task, that is to create boxes here, and you have a set of 1, 2, 3, 4, 5. You already know that as regulars in school. But if you have 2 sets, then you can create a question that is, how would you fill this? Okay, this one. Okay, but are there other ways in order to fill it instead of using this one? I take this and this. Okay, good. Are there other ways? Okay, yes, they are, and so on. So you can also teach, according to this, also the possibility that maybe you can also switch the order and you obtain always the same result. You can ask them to use different objects. For kindergarten and for the first year of the school, that could be also a reliable way to learn not only calculations, easy calculations, but also properties like the symmetrical properties of mathematics. Then you can create also situation of this kind, for example, if you would like to know what is a 3 by 4, you can create a line of 4, and then you create 3 lines of 4, and you bind them. While you are spending time in binding objects, you are thinking about what you have to do. Therefore, it's quite a slow process, and slow processes did by hand are generally remembered more than fast processes made using just your memory or your brain. Then you may think that this could be interesting for the young children, but what about older children? Well, you can create also something related to motion, and you can ask them to predict what is going to happen if you move this in this direction or in the other direction. And here the purple one would move in the same direction with respect to this one, because this has an inverted direction with respect to this gear. You can also involve motor actions, for example, by adding a mechanism so that you're not moving that with your hand. You can create also bigger movements. So, for example, by asking people to evaluate that this is a bevel. So you move on this axis, but also on the other one. So you involve a three-dimensional movements. And okay, and therefore you create a machine. But you can also create something for motor activity. For example, for the upper limbs, the shoulder, and the other part, by creating a mechanism of this kind. Therefore, you ask people to move it to evaluate what is going to happen. And it's quite, no sense, because you cannot really predict. There are 3 joints, 1, 2, and 3. But you may ask them to control it, for example, by moving just this part and leaving that steady. So you have to create a movement and to learn how to move your arm in order to control it. So mathematics, but in this case, we're talking about also physical education. The other hand, and then to control both by not moving this lateral, but just the inner part. How can you do that? Well, it's a kind of tricky, but you can still do it if you are controlling tightly your muscles. Therefore, a lot of applications, but what is more important, I don't know whether you know this, what's the representation of?
It's a house?
Maybe. From the mathematical or geometrical point of view?
Okay. Es un, I cannot say in English.
¿En español?
En español es una símil, es una similaridad, es un... Me sigue pareciendo una casa con 2 chimeneas.
Yeah, it may be a house. But if you are struggling to describe a Pythagorean theorem, then this may be a representation, because you create a square out of the diagonal of the red square, or the red triangle, and then you create 2 cubes for the 2, let's say, for the 2 sides of the triangle. And therefore, then you can easily understand that the sum of these two is congruent to this, to the square created on the diagonal of the triangle, of the red triangle. So the Pythagorean theorem. And that is a very easy thing, let's say, because you can create also more and more of them. Let's come back to the presentation in order to go straight to the finish. So you can find a lot of examples about that. And to just summarize what we had described to develop that are fine motor skills, visuospatial skills as well, and so other skills. And with all subjects in school, but what is most important is that it is a game. And you can create also, I'm sorry, I should come back to this, because you can create also other objects, a ball. Try evaluating how this is created. But then other figures that could be easy or complex figures, depending on your skills and depending on whether you have ideas. That's why I was talking about creativity. So then, why I'm talking about this? Because there are a lot of studies currently running, one or two for two PhD students that are at the end of their course, and then two projects. One that's been granted by the National Swiss Foundation, and one from the European Union, in which I'm working also with a Spanish group established in Aviles, in Asturias, that the goal is to evaluate how robotics could be made for primary and secondary schools. Then let's move on to conclusions that mathematics seems to be difficult. And I agree with a colleague of us that in the beginning described that it is difficult if people are not explaining that good to us. Obviously, I agree also with Marta, in which if you know human cognition, this may help you to know what to do. And if you're a teacher, it's quite mandatory to know how human cognition works, because you are working with other human people. And sometimes you may find that it's not necessary to explain mathematics. You can, if you can create or use materials that are to the purpose, good for the purpose, well, you are working less. Students are working less with less effort. And what are the main reasons about using this kind of material? Are oriented to a goal, because you are not just talking about abstract things. You're asking them to create something. It's you can really see what it happens, because you don't need to think about that beforehand. You may think afterwards about reasoning on something that is a material that you created. It also includes autocorrection, because also the task of filling the boxes here, you cannot fail, because you know what fits and what does not fit. You don't need a teacher to tell you, oh, that's wrong, that's correct. You can see it on your own. And this makes materials of this kind very, very easy to be used, not just in the high school, but also in the kindergarten. And here I can indicate a guest for those that are working in research, a guest issue of this journal, Sustainability, that is trying to answering to put one, maybe not the answer, but one answer to the problem described by Marta. But what's the main part of this talk is the take-home message that in little things like these cubes, well, a great satisfaction can be hidden. And this is my daughter at the age of 2.5, playing and being happy with these materials. And that's it.
Wow, great. Thank you so much, Demis. I think this is one of the most interesting speech that we have today. Thank you so much to bring this to us, to bring your research to us. And thank you, because I'm focused, or I used to hear about questionnaires measures, you know, but it's something that is really in the past. I mean, we are moving so slow through the methodologies, the new methodologies in mathematics. So with questionnaire, you can count 1 to 10, 10 to 1, and so on. But you cannot see the properties in 3D that you saw with us here. So it's so interesting, and I think this is the principle of the robotics. Maybe I don't know how the situation is in Italy, but Spain is full of extracurricular activities in robotics that are not robotics at all, are Legos or Playmobil, you know, this Arduino that is interesting, but yeah, but it's interesting, but they are not creating this brain genius boy that the parents are expecting. And I think if you allowed me this comparison or this link, we can link your speech with the last part of mine, when I said that the neuroeducation is not the result, is the process, is the teach-learning process. So these robotic curriculum activities that are sending or that are selling in the front part of the schools are result. They are looking for the genius. They are looking for the little genius inside the little minds of our kids, but they are not focused on the process. And your little blocks are focused on this process, this manipulating, this explore, and the motivation, of course, because this is a play. This is playing, and this is how kids have to learn. So I'm so impressed. Thank you so much. And now in Spanish, a little sum up. Le estaba diciendo a Demis que estoy muy impresionada con su charla, porque bueno, estamos muy acostumbrados a oír hablar de los bloques lógicos, sí, y de las reglas de Questionnaire, pero uy, por ahí se ha colado un micro. Voy a silenciaros. A ver. Ya está. Bueno, perdón, que está diciendo que estamos acostumbrados a las regletas de Questionnaire, que son algo, pues, un poco del pasado, y que puedes contar de 1 a 10, de 10 a 1, pero al final esa manipulación que nos ha enseñado, esas reglas matemáticas que hay detrás, pues le decía que me permitía el lujo de vincular un poquito el final de mi charla con la suya y hablar de que la neuroeducación está en el proceso. Hay muchas actividades extraescolares en robótica que no son robótica del todo, son unos legos que se mueven, que molan un montón, que son geniales, pero se olvidan de ese proceso, del proceso de enseñanza-aprendizaje que buscamos en esa neuroeducación. No estamos buscando al niño genio, no estamos buscando que la evaluación del niño sea perfecta, ni que adelantemos sus procesos o sus conocimientos, mejor dicho, para que sean el 10 en matemáticas. Esto no se trata de buscar el 10 en matemáticas, sino de conocer qué está pasando en nuestro desarrollo neurológico, que podemos volcar en unas pequeñas piezas que nos ayudan a tocar las matemáticas. Esto está muy implicado con el desarrollo motor, evidentemente, y está muy bien vinculada a la charla, a mí me ha encantado. Así que no sé si hay alguna pregunta, pero yo estoy encantada.